So in this video, we're going to look at problems 2 through 4 of the practice exam. We have an individual riding on a seat. We're given the weight of him along with the chair itself, and we're asked to find the tension in the various cables that support this individual. And if you notice in this scenario, there are two cables, one passing underneath the actual pulley and one that's fastened directly to the middle of the pulley. So we want to draw our free body diagram in such a way that we basically cut the cables. And the reason we want to cut the cables is when we draw the free body diagram, we will replace the effect of drawing those cables by unknown forces that describe the quantities of interest that we're interested in. So when we make this segmentation here, since we've removed this individual and the pulley from that rope, we have to replace the effect of the rope by noting that it is pulling it up and to the right along this angle beta. So in a similar fashion, we'll add tensions for each of the effects of the cables that we've segmented. The key thing in this, and if you watched the video originally, you noticed that I wasn't paying attention when I did the original problem, and I ignored that second cable. The cable that is passing underneath the pulley is the same cable. So by definition, it can only have one tension inside of it. So even though the forces that it's exerting on each side of the pulley have different directions, alpha and beta, their magnitudes are the same. So that's all that this is saying here, is that the magnitude of this force and the magnitude of this force are the same because it's the same rope, and the rope has to be in the same tension. So once you have this free body diagram with the four forces acting upon it, the next thing you need to do is to decompose each force into rectangular components. These are pretty easy to do. TCB going to the right at an angle of beta. The X component will just be TCB cos beta. The Y component will be TCB sine theta. Be careful with these two going to the left that you manually adjust their X components to be negative. Of course, the Y components are still positive. And of course, for the weight itself, there is no X component to that force. It is purely in the negative Y direction. So we'll denote that as negative W times J. So what you want to do next is write your equations of equilibrium that say the sum of all forces in the X direction must be zero, along with the sum of all forces in the Y direction. Note that for both the X and Y forces, when you add the components associated with the forces of that same cable, TACB, that you're going to be able to factor that out as a common factor that you don't know. So TCB and TCA, the magnitude of both of those forces is TACB. So when you add the X components, for example, you're adding one term that involves TACB to another term that involves TACB. You're adding a negative, so it's effectively subtracting. When you factor that unknown out, this will allow you to set it up in 2x2 system form, where the unknowns are actually TACB and TCD. So again, you're going to know alpha and you're going to know beta. You're going to be able to plug these numbers in, and you're just going to have coefficients here. You'll also know W, the combined weight of the sailor and chair. So you can write this as a 2x2 linear system that can be solved in MATLAB for the two unknowns, that tension in cable ACB along with the tension in cable CD.